Hello, and welcome to my talk about Chrome IPC and Chrome exploitation, coming from an exploit render from a compromised renderer. And actually, the bug that I will be using as an example is the one that Ned just talked about. So you now heard about a lot about discovering bugs, and this is more going to be about exploit primitives and actually writing an exploit for Chrome. So Ned found this bug in July last year. And he wanted to participate in the Hack to Win contest, which was in September. But for that, he needed a full exploit for this. And since there was a pretty short amount of time left, we decided to join forces on that and write the exploit together. And at that point, our target was Windows here, and Ned had never done any Windows exploitation, while I never had done any Chrome exploitation. So it was so we both learned a lot from that. So this talk is going to be about how we approach this problem. Coming from a bit of a lacking knowledge base because we've never really done work in this area before. And hopefully you will find it useful maybe for your own bugs. Just a quick recap about how the Chrome Sandbox looks like. This is on Windows, but you will find a very similar architecture on other platforms, the most important obviously being Android. Since the whole meltdown in Spectre, Chrome introduced site isolation, which means that you have at least one render process per site. And these processes are responsible for parsing HTML, executing JavaScript, and doing all the very dangerous file parsing stuff. So they're heavily sandboxed, which on Windows means that they essentially have a security token that's not allowed to do anything. And most of the kernel attack surface is completely locked down. But of course, there needs to be some way to do cross-origin operations, to do networking, talk to the outside world, render the UI, and so on. And that's the responsibility of the browser process, of which there's only one, and which is highly privileged. So it doesn't run in a sandbox at all. And if you compromise it, you get a normal code execution as the user who's running Chrome. There's also a GPU process that does compositing, but I'm not going to be concerned with that too much here. So yeah, if you think about what can you do when you compromise a renderer and you want to escape from the Chrome sandbox, there's the kernel. There's maybe some system services that you can talk to or other mechanisms of doing IPC with components outside of Chrome. But also there is this big layer of functionality exposed by the browser process to the renderer in order to do essentially everything that the renderers can't do themselves. And there's at least two IPC mechanisms that Chrome uses. One is the legacy Chromium IPC. It's still used for a lot of services. And then they have a new implementation of IPC, which is called Mojo, which has supposedly better state management, especially when it comes to the shutdown sequence, and is more performant overall. And they were starting to move services towards that, and a lot of them are implemented in Mojo at this point. Now, the really cool thing about this attack surface is that you can find bugs that work on all platforms here. So, I mean, especially on Windows and Android, which are the most important platforms for Chrome, maybe if you find a bug, due to various circumstances, could be that it might only be exploitable on one of these platforms. So you have double the chance of success in that sense. Also, I would say at this point, there's probably more attack surface here than there is actually in the kernel, because we can't really do much with the kernel. And at least on Windows, it's important that from an exploitation perspective, we're exploiting userland to userland. And that means, for example, that all the modules are loaded at the same address. So we don't have to concern ourselves with ASLR. We don't need extra infraleaks to break ASLR, at least on Windows. And also, there is no CFG, for example, which would be there in the kernel. Okay, so Ned didn't really tell you what the bug was that he found. So I'm just going to introduce that to you. And for that, I need to actually explain to you a bit what application cache is. It's a feature to enable offline web applications. And of course, if you want your website to be available offline, you also need all the resources that the website uses to be available offline. And app cache gives you a way to specify which resources you want to be there in the cache 100% of the time. So here in this example, you have an HTML file, which includes an image. And this image file is also part of an app cache manifest that this document references. And this manifest tells the browser to cache this resource. Actually, you can also specify stuff that's not supposed to be cached. For example, because it's dynamic and it cannot be made available offline. Some quick terminology. This HTML document that you saw, in the spec, this would be called a cache host. And you can, of course, have several of these if you have several documents loaded. And then you will have one so-called cache group per manifest file that these reference. And in this example here, both documents actually specify the same manifest, so you have one group with 2 hosts. And then you can imagine that maybe over time, the developer will add more stuff to this manifest or change resources that are specified in the manifest. So there can be different versions of this cache that represent different points in time where these resources were fetched. And these are called caches. And you will have several of these per group. All right. So this is the IPC interface. Ned already showed it quickly. What's important here is we can register hosts, we can delete hosts, and we can tell the backend what manifest a host specified. Because that's in HTML, so the renderer knows about it, but the browser also needs to know about it. So this is used, for this we can use the select cache function. So all of these types of objects are reference counted. And with reference counting, you will always need to ask the question, what are the ownership semantics? Who's keeping what alive, or who owns what? And in order to keep something alive in that sense, you need a so-called strong pointer to an object, which is a pointer that increments the ref count by 1, and thus prevents the object from being freed. And you would expect maybe that in this example, that this app cache group that has several versions, maybe it will just own all of these versions, but it's actually not the case. As you can see on the right here, it's the other way around. Every version has a strong pointer to its group, and not vice versa. But there is a special, there's a weak pointer, however, from the group to its newest version. But that's not keeping anything alive. Otherwise, you would have a cyclic reference here, and nothing would ever get freed. So this black arrow here is a weak reference. And also, every host will have a strong pointer to the version of the cache that it uses. But the question is, okay, what if none of the hosts actually are on the newest version? Then who's holding on to that newest version? And for that, there's an extra strong pointer that every host has, which specifically points to the newest version. So this is how this newest version will stay alive, and this is important to understand this bug. Now, what Ned's fuzzer found was a magic sequence of IPC calls. And I say magic because none of us really understand how it works. But it was founded by a fuzzer, so we don't really care. And that's the cool thing about fuzzing. And what it does is it puts this group into an update state where it will refetch the manifest, check if there's any new resources, and so on. And during that time, instead of having a strong pointer to this newest version, all of the hosts will be in a waiting state, waiting for an event to be delivered by the group saying, hey, this update is finished, and you can go back to your normal state. But what's curious here, although everything is in use really, nobody's really holding on to this whole right side here anymore. And this means that the app caches get freed, and that the group gets freed. And what happens when the group gets deleted, it enters its destructor, and it will notify the hosts that the update is finished. In this case, it's actually canceled. So this event listener will be called, and the hosts go back to the normal state by copying this weak pointer to the newest version and adding a new strong reference. But this is bad because this app cache is deleted now, but now we have a strong reference to a dead object. So, and actually we have many of these hosts, as many as we want, so we can have as many strong references to this dead object as we want. And now if we delete these hosts, the strong pointer will also get deleted, and because a use after free situation specifically, we will decrement the ref count on a freed object. And we can do this as many times as we want because we can have as many hosts as we want. And if this ref count ever goes to 0, obviously the object is going to be destroyed. So we enter the destructor again, but this time it would be a use after free object. So our first analysis was that, okay, this seems pretty trivial. We have no ASLR because it's Windows, and the modules will be in the same place as they are in the renderer. We also found very quickly a primitive to allocate arbitrary data, and we could reclaim the app cache object with that. But the problem is, app cache is not a virtual class, so we can't just hijack the vtable. And also it contains pointers to other objects that will be dereferenced in the destructor, so we cannot survive the destructor without faking these pointers. So we knew that we needed an extra info leak. Okay, so what info do we need for this? Well, maybe we can place this fake object that we need a pointer to somewhere on the heap, and then we leak its location, like this. But this would not be enough, because this fake object in turn has other pointers, and these need to be valid as well. So at the time when we placed this object, we didn't know what to put as the second order pointer. So either we find something where we can change the data after and fix up the pointer, or we can get away with some sort of heap spray where we just predict where something will end up. So this is what we ended up doing. Let's say this is the heap going upwards. We know that the allocator will allocate from this point on upwards. So now we leak a heap pointer, any heap pointer really, and I'll tell you later how. It points somewhere near the close, towards the top of the heap. And now if we spray some, say, 400 megabytes of data, and we just add a constant to this and round it down to page size, we have a pointer into our heap spray. So this way we can, if we just repeat our fake object now in every single page that we spray, then this pointer will surely point into one of these pages. And now the heap spray is actually, I think, a very generic primitive, which is useful in general for exploitation. And we use blobs for that. They're essentially just binary data that you can get a URL for. As you can see here in this example, I'm creating a blob that has two parts. So the actual blob data would be hello world. We can specify a MIME type. And if we want, we can generate a URL with which we can reference this blob. And we can also pass this URL around to another site, for example. And because of this, it needs to be some sort of cross-site object handled by the browser process. And in fact, if we just do this, if we just call this blob constructor, it will just be on the browser heap with no header or footer. We can control the size, and we can control the contents fully. So this is a really good primitive. In our experiments, it works up to a size of 8 megabytes. And if we spray enough of these, you will end up with a heap looking like this. This might be hard to read, but in yellow I marked all the blobs that ended up being on the heap, and in between you have some unmapped space, which is small enough that the likelihood that if you pick any of the addresses here, that you hit one of the map pages from a blob is pretty high, and probably can be made even higher by doing a bit more careful spraying. And we use the same primitive to reclaim the space used by the app cache at the end to get code execution. Okay, so we need an info leak now, but we don't really need to leak anything specific, just any heap pointer really. And of course, the first thing you do is look at the object that you actually use after freeing. In this case, the app cache. And it would have probably been possible to turn this use after free into a situation where it would send an address back to the renderer, but it didn't seem very robust or generic, and also it would have involved much more magic IPC call sequences, which are just a mess to deal with. So instead, we were looking for other objects that had the exact same size, so they would land in the same heap bucket on Windows, and we could reclaim the space of the app cache with it. I think one good way to do it would be to use a Clang plugin and dump all the types that have the correct size. What we tried first is just to do a quick hack using WinDBG, using the dt-s command to filter types by size. And it turned out that one of these was actually good enough for us already. It's called a canonical cookie. And this object has not exactly the same size as an app cache. It's 8 byte larger, but it will land in the same spot. And it has as the first member the name of the cookie. And this is a string which in turn has as its first member a pointer to the string data. And with our decrement primitive, we could decrement that pointer so that it would point lower in the heap. And now if we read back all the cookies from the renderer, we get a cookie that has a name with a lot of 0 bytes and some interesting heap pointers in it. So this is what we ended up doing in the end. But before we found this, we also looked at some other options, which would have been more generic. So I just want to show you these. For example, you can look for C++ vectors that have a variable size that where you can control the size as a renderer, because that means you can make it as large as you want, and you can reclaim anything you want with it. Again, we didn't use a Clang plugin, which would have been the correct way to do it. Instead, we just did some guessing, and Ned used some regexes to search through the code base. One thing that we found was the second one here. It's a class called the blob reader, and it's again related to the blobs that I showed earlier. And it pre-computes a list of it pre-computes for the parts that the blob consists of. It pre-computes the size, so that later when you read from a specific offset, it can just go through this list and see what part this is in. So that means later it will trust these size values that are stored inside this vector to know how long a blob is. And if we can increment one of these integers, and I guess with a lot of memory corruption primitives that you could imagine, you could maybe increment some value here, you would get an info leak as well. Unfortunately, we could specifically only decrement a value, so we couldn't use this. Yeah, one thing I noticed when writing this exploit together with Ned is that we really needed to evaluate a lot of ideas very quickly, and we needed to throw away as many bad ideas as possible, as quickly as possible. And instead of writing all the exploits to try these things, what we did is we just modeled the end result of what we wanted to achieve with some exploit primitive using Frida. And this way we could just see if something worked before we had to implement it. And this way we could just iterate much faster on the exploit and collaborate better because we could parallelize different stages of the exploit. Yeah, the good thing here is that we can verify every assumption that we make from highest to lowest risk. So if you know something that maybe we'll need to do at the end of the exploit, but we don't really know if it works, or we're very skeptical that it will work, then maybe we should try to verify that this works in the very beginning without actually writing the full exploit. Okay, so also this was a full chain because we staged it on a renderer exploit by Samuel Groß. And how do you even write a sandbox escape in a renderer? How do you even load your code? Like, how do you even write this exploit? So one thing you could do is you just write the whole exploit in C and somehow manage to compile that C down to shellcode and then run that shellcode in the renderer. I personally like to write most of it in JavaScript if possible. So we did a combination of the two things. We actually loaded C++ code in memory by getting shellcode execution using something called reflective DLL injection, which you can just find the source code for online. And then the C++ code, it would expose certain primitives to the JavaScript code so that we can then write the exploit in JavaScript. Also, if we're doing this, then we need our exploit to be good enough that we can actually execute JavaScript after we get shellcode execution. And since Samu's bug was actually a JavaScript engine bug, what we ended up doing is instead of doing all the continuation dance and fixing up everything, we just ran the exploit in a separate thread using web workers. And then at the end of the shellcode, which did some patching and stuff, it would just go into an infinite loop, and the other thread could continue executing JavaScript. So I think that's a neat trick to make your life a lot easier. So what does the C++ code actually do? First of all, it would apply some renderer patches that we needed, for example, to read back the cookies. But most importantly, it would hook one of the JavaScript standard library functions so that we could call from JavaScript into C++. And then through that hook, the C++ code exposed some native functionality to the JavaScript code. For example, to look up the so-called cache host proxy object, which you can call all these IPC functions on, like register host and so on that I showed earlier. So this native code, it will just follow a bunch of pointers to get to this proxy object, and then it will call our IPC functions directly on it. So we didn't even have to bother with implementing Mojo in any way or form, because we just used it as a black box. We just used the implementation that's already there in the renderer. Of course, this only worked because we were actually exploiting a bug in a Mojo service. If we wanted to exploit a bug in Mojo itself, then probably we would have to either re-implement parts of it or patch the implementation that's there to trigger whatever other bug we have in Mojo itself. All right, this is a quick demo. I mean, browser exploit demos are quite boring, but still, there will a calc will pop. Maybe, yeah. So here we trigger the bug 3 times. Once to get an info leak, it didn't work, then we try that again. And then we leak a bunch of heap data. We have a heuristic that detects pointers in there. And then we trigger it a 3rd time to get code execution. Yeah, so, I mean, yeah, that's it from my end. You can actually find the whole exploit online on GitHub if you want to study it. Especially, I think the most reusable parts of it are the C++ implementation that's doing the hooking, so you can call from JavaScript to C++, and the whole heap spraying business. And feel free to I don't know, ask questions about it. If you're studying it and you have questions, feel free to ping me on Twitter or something. And of course, if you're interested in discovery, you just listen to the talk that Ned just gave. But there's also a write-up in the Google documentation. I don't know for what exactly, about structure-aware fuzzing and how this fuzzer was developed. Okay, so that's it from me, and feel free to ask any questions now.
Do we have questions?
All right, so if any questions come up later, you can find me around here.
Okay, thank you then.